Hi, welcome. So in the last video, we stopped at lecture 5 and now we'll just save this as lecture 6. Okay, the last video we were talking about how in the finite square well, um, you have the wave functions or the matter waves, so to speak, they're leaking out because it's a finite potential well. Okay, I tried to explain it using guitar strings and all, but yeah, you'll be able to see more in these Libre texts, physics and the physics Libre texts. These are also CC Creative Commons license, means someone has um, allowed me to copy and redistribute material in any medium for any format or purpose, and even remix, transform, and build upon the material for any purpose, even commercial purposes. So yeah, these are very useful free texts that you can use to look at the math, so to speak. And yeah, of course, this may not make much sense to you if you're not familiar, but these are the reference materials I will be using. Okay, so without further ado, let's start. So the last time we were talking about finite potential wells and how that contributes to this quantum tunneling phenomena because these particles leak through the barrier, or rather the wave nature of these particles allows them to leak through the barrier. Okay, the wave nature of electrons and protons, neutrons allows them to leak through the barrier. In fact, whole alpha particles can leak through the barrier. Okay, so yeah, just writing lecture 6 first. So yeah, the infinite square well gives us the idea that there are discrete energy levels. The finite square well, or the finite well, or the simple harmonic oscillator allows us to see that, okay, mathematically speaking, these waves can leak through finite barriers. Okay, even though normally in a particle sense it doesn't make sense, but in a wave sense it makes sense. All right, so these are the two insights that these things have given us. Okay, Schrodinger's equation has given us these simplified versions of simplified what do you call that? Simplified scenarios such as the infinite 1D square well. Then we kind of made it a little bit more realistic by using a finite force field or finite well. Okay, such as a simple harmonic oscillator or even just a finite square well also kind of works. Okay, of course, the other simplification that we made is that the last in the math sense we only describe 1D waves. Okay, reality is not so simple. Okay, in previous discussion we talk about 1D waves. These are sine and cosine waves. Okay, normally sine and cosine waves or even or exponentials. Okay, so this is a very simple sine wave. Okay, y equals to sine of x. So reality is, okay, we need to deal with 1D. Well, reality is 1D geometry is not representative. Is not representative of an atom or nucleus. Okay, we need 3D, a 3D version. Okay, yeah, we need 3D version. That's just how the world works or how physics works. And not just any 3D, we have to pay attention to the shape of the force field. Okay, the shape of the force field was determined by the electric force. Okay, Q1, Q2 over 4 pi epsilon r square. There's basically some constant multiplied by the charges, but the r squared itself, um, the r squared itself actually makes it, it is hinting to you that it's a circular or spherical shape. Okay, force fields are spherical, are governed by spherical shapes, or rather, I'll say spherical in nature. In nature. Okay, so the force is proportional to 1 over 4 pi epsilon naught r squared. So this 4 pi r squared, this is a circle. Okay, this is a spherical area. Okay, sphere surface area equals to 4 pi r squared. If you recall, maybe I'm just giving you some insights into the math, but I don't really want to do the math right here. I'm just saying that, hey, these force fields are spherical in nature, therefore we need a spherical version of a sine wave. We need a spherical version of the sine wave. Okay, so if you are again concerned about this, okay, spherical harmonics is the topic we want to briefly discuss, not mathematically, but inevitably there's some you have to foray a little bit into math. I'm not going to do the math, but I'm just going to introduce you to it a little bit, talk about it, that's all. Just give you some insight or intuition into what it means. Okay, spherical harmonics. Okay, these are just the 3D spherical version of a sine wave. Okay, these are just 3D spherical version of sine waves. Of course, I may be oversimplifying things, but that's how I like to think about it. Okay, spherical harmonics. So, let's see. Where is my... Yes. There you go, there you go. Come on. Yeah. So the Schrodinger equation, when you talk about spheres, spherical harmonics, is it you will usually look at it in context of a hydrogen atom. Why hydrogen atom specifically? Okay, because hydrogen atom is basically the simplest atom there is. Okay, so this spherical harmonics is explored in hydrogen atom. Okay, where there's just one proton in the center. And then so-called the electrons, they will be smeared out in a wave. Is a wave, a 3D matter wave. Okay, so this is the electron cloud. We like to call it the electron cloud. Okay, so one proton in the center and one electron forming a cloud-like thingy. Okay, so that's basically what it means. Okay, this is all the math that you're seeing here. Is all of this is how we kind of derive the spherical harmonics. So I will not delve too much into it, except I'll just tell you, after you do all the math magic, this is what happens. Okay, after you do all the math magic, this is what happens. Where's my... Yes. Save this. I'll just tell you the implications, yeah? Implications of spherical harmonics. Okay. One thing is that angular momentum becomes important. Let me use blue. Momentum becomes important. So this is actually governed by the number L in the spherical harmonics. So if you look here, you see this L here. This L is usually we see this L right here, I'm highlighting. Those L's usually are quantum numbers. You just numbers, the L number in the spherical harmonics. This has to do with uh, angular momentum. Okay, see this three integer quantum numbers n, l, and n. So n here deals with energy levels. L deals with the uh, angular momentum. Okay, if you actually look at the physics libre text here, okay, L here is angular momentum. Okay, okay, principal quantum number is n. Angular momentum orbital quantum number, that is L. So angular momentum becomes important. Okay, in the 1D case, there's no angular momentum because you only move in the x direction. But in the 3D case, where you talk about 3D case in a spherical geometry, angular momentum now becomes an important factor as to how these waves vibrate, so to speak. Okay, so angular momentum will change the shape of the wave in 3D. Okay, not only that, there's this thing called angular momentum projection quantum number, which is basically the way, if you take a look here, you can actually see that angular momentum, this L is a vector. So depending where you point the L, okay, depending where you point the L, that M quantum number will change. And in some texts, you may also see that this may be correlated to the magnetic angular magnetic moment or something to the effect. But this M number. Okay, so this M number is that projection of the angular momentum. L is the angular momentum. Right. So these three numbers are very important, and these come out of spherical harmonics. Okay. So let's do this one. Okay. Angular momentum projection number becomes important. And that's this M number here. Now the N number is called the principal quantum number. Basically, it just gives us the energy level, the general energy level of the electron wave. That is what describes how the wave is vibrating. But now we move to 3D, we have two additional quantum numbers that come about, and these deal with the angular momentum and its projection, or maybe we might even think of it as a magnetic moment sort of thing. Okay, so I'm just saying that in 3D now, instead of just energy level, you have these two other things to think about. So that's what spherical harmonics does for you. So how does the wave look like in 3D? Okay, so let me just let me give you the 1D version and the 3D version. Okay, 1D version, the fundamental wave looks like this. So it's like a band going up and down. This is the fundamental node. Okay, is this n equals to 1? Yeah, I think that's n equals to 1. Okay, this is called n equals to 1. This is the principal quantum number. In 3D, how do you have this vibration in 3D? So basically, the most simple shape is just that of a sphere. Okay, a spherical shape. Okay, it is the most dense, so to speak, in the center, and then it gets more and more like sparse. The vibrations become more sparse outside. That's how you think about it. This is the n equals 1 equivalent in 3D. So this is called, sometimes it's called the s orbital. If you take chemistry, this is where the s orbital comes from. It's the lowest mode, lowest energy. Now what's n equals 2 look like? Okay, n equals 2 looks like this. So one full sine wave, so to speak, one full sine wave. Okay, in the 1D version, it looks like this, and this is the so-called node where there's no vibration. Okay, I'm using the infinite square well sine and cosine waves for simplicity, yeah, but Of course, there's the finite square well, or not finite, finite well complexity we need to add in, not simplification. Okay, but anyway, the rough shape is like this. Okay, how does it go into 3D? Okay, the 3D version is like this. It looks like an infinite shape. Okay, and of course, yeah, you will have the vibrations, so-called, so to speak, at these ends. Okay, I can't exactly remember how it looks like, but how the electron densities are like, but it looks like a dumbbell. If you can see the 1D projection in 3D, this is sort of what it looks like. We call this p orbitals. We call this p orbitals. So you can see somewhat the 1D and the 3D, the projection kind of looks a bit like that. Okay, it kind of looks a bit like that. So let's go to this hydrogen atom, and this is what this p orbital here looks like. It's really like a dumbbell. Okay, this is the s orbital. This is the p orbital. There are higher versions of it as well. Higher versions where you have higher modes. So this is the what we call the probability clouds. That's not just the wave, but you square the wave as well. Okay, so this is the d orbital. The third one is called d, but it gets more and more complex the further the higher energy level you have. Okay, so that's what these orbitals look like. And what I'm trying to say is that uh what is true of the electrons, and this is at least for the nuclear physics context. Uh, it's from black. So in spherical harmonics, okay, in spherical harmonics, okay, spherical harmonics, you need three numbers, okay, n, l, and m. Okay, this become important. Okay, the n, l, and m become important. Let's see. So this is n equals to 2 and l equals to 1. This is the classic p orbital. P orbital. So yeah, this is a p orbital. Okay, right. So I think I forgot to mention this angular momentum things they came into play. All right. So I forgot to put this in. Okay, so what I'm drawing here is kind of an oversimplification, but I hope it just helps you get an idea. So over here, there's no L. There's no L. Okay, here L becomes a factor. Okay, in the lowest, n equals to 1, L over here equals to 0. Okay, so this is the s orbital. S orbitals are usually when L equals to 0, but the p orbitals are when L equals to 1. Okay, you have some momentum, and depending on the projection of this angular momentum, you have it aligned along the x, along the y, along the z axis. That is the m number I'm talking about. Okay, that's the m number. Okay, so yeah, that if my memory doesn't fail me, that m number is that projection, the azimuthal. How do you rotate these distributions? Okay, so we like to call that px, py, pz in chemistry, because how does this electron orbitals relate to chemistry? So electrons, the study of electrons, how they flow from one atom to another, that is the whole basis of chemistry. All of it comes from the Schrodinger equation. Okay, so there is this very big crossover between physics and chemistry when you talk about electron orbitals. Okay, so now okay, now before I forget, yes, you can have n equals to 2 and l equals to 0 as well. There's the l equals to 0. Okay, for n equals to 2, I'm not going to draw it here. It is also an s orbital. Okay, it's also an s orbital. So that's where the analogy sort of just breaks down when you start going into the n equals to 2, where angular momentum starts becoming important. But I'm just hoping from this what I'm showing you here, there is some correlation between what you see in the 1D and then how it sort of translates to a 3D. It's not 100% accurate. I just hope to give you an idea. Okay, very hand wavy idea. Okay, so all this applies to electrons, and in spherical harmonics, this NL and M number becomes quite important in electrons. Okay, and the same applies to the nucleus. Okay, same applies to the nucleus. That means protons and neutrons. So the same equation that governs this electron cloud is the same equation that deals with these protons and neutrons. Except the force field, even though it's spherical, the force field for the nucleus is not the electric force anymore. Electronic repulsion and attraction is not there anymore. It becomes the strong nuclear force. So that's the main difference. Strong nuclear force, you can think of it as a very short range glue. Okay. In fact, if you study particle physics, I've heard of it being referred to as the gluon. Okay. Strong nuclear force. Force is responsible for force fields rather than electric. Okay, so electric force actually, yeah, it plays a little bit of role, but most of it is dominated by the strong nuclear force. Why does electric force play a role in this nuclear physics? Because the protons actually repel each other within the nucleus. However, the strong nuclear force is stronger than these protons. Okay, but the same spherical harmonics equations will apply here, except where the force field shape, the force field profile is kind of different for the electrons and the protons and neutrons. Okay, each of them have a different force field shape. Yeah, so the electrons have a shape, protons have a shape, neutrons have a shape. Okay, so that's what I'm trying to say with this spherical harmonics. Okay, so let's before we move on, let's summarize what happened so far based on this mathematical exploration into Schrodinger's equation. Okay, so you see the spherical harmonics actually comes down to this. It comes down to these few wave functions. In fact, you can see in spherical harmonics, there's a cosine and a sine function here as well. There's some exponentials as well. So all of these, they do sort of play a role. Okay, so the cosines and exponentials, they will still be there. Okay, but there's a lot more into it than just sines and cosines. That's what I'm trying to say. Okay, so summary. Let's just do a summary. Okay, based on Schrodinger's equation. So there's implications of Schrodinger's equation. Okay, pardon the handwriting. So first thing first, we studied the infinite square well. This is the most mathematically simple, or rather we didn't even go through the math, but we just took a look at it conceptually. Infinite square well, and that tells you what? From this we learned that we have energy levels, discrete energy levels. Discrete energy levels. That's the infinite square well. Okay, second we do a finite well. Okay, such as the simple harmonic oscillator. Okay, what this shows you from the math. Okay, it gives you a basis for quantum tunneling in addition to what we already have. Okay, in addition to the discrete energy levels we had before, we now have quantum tunneling because these waves sort of leak out as we covered it before. Third is that we go from 1D to 3D, spherical harmonics. Okay, and what's the implication here? Okay, angular momentum, L, okay, angular momentum becomes important. And the M number, angular momentum projection, and this is also related to the magnetic moment, if I'm not wrong. Projection, this also becomes important. So all that has to do with all the math and the derivatives and all, but I'm just taking out the math and I'm saying after you do all that math magic, these are the implication. Discrete energy levels, you have quantum tunneling, you have these angular momentum thingies that become important because of the math. So I hope this gives you some insight as to how one might think in the quantum, doing quantum mechanics or quantum mechanics. Yeah. So all this is the foundational baseline which you need to understand nuclear physics. That's the most basic. Okay. Once you have this in your toolbox, you should be able to understand you should be in a better place to understand nuclear physics. Okay. You know, there's still some things you need to learn along the way, but this is your foundational toolbox. Okay, so I'll stop for now. Thanks for watching. I'll see you guys next time.